Welcome to the problem solving sessions for week 12. I am Shreya, one of the TAs for this course, and today I'll be discussing week 12 lectures. So before that, am I audible and is the screen visible? Okay, fine, so let's get started. Okay, so in the previous classes we learnt about multiple linear regression. So and we also learned about how to conduct how to get the estimates of the regression coefficients. Okay, we learned about two methods. One is the methods of least squares. The next one was maximum likelihood. This was with respect to estimation, and then we also learned about test of hypothesis. Okay, where we wanted to check whether an independent variable is significant or not, or in the sense that whether it is important in the model or not. And as a continuation to this, we also learned about confidence intervals. All right, now apart from these, we also learned about some properties of the estimators that we were using, of basically the OLS estimators, that whether they are unbiased or not, whether they have minimum variance or not, under what conditions they what are the assumptions under which these have been derived, and so on and so forth. So ultimately, in this class today, or this session, we would know more about analysis of variance and some other regularized regressions. Okay, so in week 12 we started with a topic called analysis of variance. Now, what is this and why is this important? So just imagine if we have a model like this where y is my response and I have x1, x2, xk, or let me write it as k minus 1 just to be at par with the lecture notes. So if y is my response or dependent and these is my set of independent variables and I want to model them. Now what I am essentially doing is that if the variation that is there in y, I am trying to capture that variation with variations due to these independent variables or independent factors. So what I am essentially doing over here is that if I have variance of y, or I shouldn't write variance of I should, so what I'm essentially doing is that I'm trying to capture the variation, total variation that is present in this y variable by the total variation that can be captured with the help of these k minus 1 independent variables. Now the thing is that if these variables are significant or important enough or good enough in explaining the variance in y, then only this sort of modeling is going to make sense. Okay, so this is, by this analysis of variance, we are trying to test for this could serve as a global test of model adequacy. Okay, so whether I want to check if these variables are sufficient, or I shouldn't say sufficient, do help in explaining the variance in y, or in other sense, these variables, whether or not they contribute significantly to the variation in y. And this sort of a testing framework is actually known as analysis of variance. Alright, so the goal here is to partition the variation in response into two independent, or I should say orthogonal components. Okay, so if I have a model like this, y equal to x beta plus epsilon, then I want from here, I want to write something like this, that variation of y is equal to variation due to the regression plus variation that is not captured by the regression. So this part is the explained variation explained by the fitted model, and this part is actually the unexplained variation. Which could be because of unaccounted factors that are not represented in this model, plus some random disturbances. Okay, so here we write this thing as SS total equal to SS sum of squares due to regression plus sum of squares due to residuals. Okay, so how is this accounted for? So sum of squares due to total is nothing but this is y transpose y, or in other words, summation I equal to 1 to n yi square divided by sum of squares due to total is actually given by summation yi minus y bar whole square, I equal to 1 to n. This thing I can write as summation yi square minus 2 y bar summation yi plus in y bar square. So this is actually summation yi square minus in y bar square. So this I can write as y transpose y minus y bar is 1 by n summation yi whole square into n. So this translates to y transpose y minus summation yi whole square by n. Okay, and then SS total is equal to y transpose y minus summation yi whole square by n. This is equal to SS due to regression plus SS due to residuals. Okay, SS due to regression is given by beta hat transpose x transpose y minus summation yi whole square divided by n. Okay, and sum of squares due to residuals is, and whereas beta hat is given by what? Beta hat is equal to the OLS, that is x transpose x inverse x transpose y. Okay, and sum of squares due to residuals is given by y minus x beta hat transpose into y minus x beta hat, which literally translates to y transpose y minus beta transpose x transpose y. Okay, now whenever I am doing a regression, multiple regression problem, if I have something like this, y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta k minus 1 xk plus epsilon, and I have something like this, SS total equal to SS regression plus SS residuals, then we'll have to remember the SST, the corresponding DF is always n minus 1. Okay, and SS due to residuals is actually n minus number of unknown parameters. So here we have, what are the unknown parameters? So these are the number of unknown parameters are this beta naught, beta 1, beta 2, beta k minus 1. So we have in total k unknown parameters. So this one will be k. Alright, and since these are additive, n minus 1 and n minus k, so this one will be, so the degrees of freedom for this one would be k minus 1. Okay, so whenever you are presented with a regression equation, regression model, a fitted model, or a regression model that you have to fit, just remember, whenever you're partitioning the variance, the sum of squares total will always have a degrees of freedom n minus 1, because if you remember here, SST is summation yi minus y bar whole square. So if we have, let's say, 10 values of yi, then knowing 9 values of y is sufficient, because the 10th value can be deduced from the value of y bar itself. So the degrees of freedom is actually not 10 but actually 9. So that is the reason we have n minus 1 as df for the sum of squares due to total, and sum of squares due to residuals is actually n minus number of unknown parameters. So if you had here p parameters, beta naught to beta p, then you would have had p plus 1 or something like that. So number of unknown betas, that are beta or whatever is the letter that you use, so number of unknown parameters, that thing is actually your sum of squares due to residuals. Okay, and k minus 1 is going to be your sum of squares due to regression. So this can also be translated to a simple linear regression. So in case of a simple linear regression, if we have let's say, so in case of simple linear regression, we have y equal to beta naught plus beta 1 x1 plus epsilon, something like this. So SST is equal to SS due to regression plus SS due to residuals. Okay, here we have n minus 1 as degrees of freedom. Here we have n minus number of unknown parameters is 2. Okay, so here we have n minus 2, because here k is actually 2, and here we have k minus 1, that is 1. And you see all of, the right hand side df adds up to n minus 1. Okay, so this is how you are going to partition the total sum of squares into two orthogonal components, and this is how their df's are going to look like. Okay, so now once you have the sum of squares due to everything, the next step is to calculate something called mean square. Okay, so mean square by general is sum of squares divided by df. Okay, so if I want to write mean square due to regression, this would be SS due to regression divided by k minus 1. And if I want to write here mean square due to residuals. This is SS residuals divided by n minus k. Remember, the model in this case is y equal to beta naught plus beta 1 x1 plus beta k minus 1 xk minus 1 plus epsilon. Okay. And if I want to find out the mean square due to jth x or xj, that would be SS due to xj divided by 1. Okay. So now that we have defined mean squares, let us find out how to actually conduct the test of significance of the regression, or in other words, this is also called analysis of variance. Okay, so here the H naught, the model is this much. So I'll just rewrite, model is y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta k minus 1 xk minus 1 plus epsilon. Okay, so this is the model, and testing of significance of the regression means that whatever explanatory variable I am considering, those are actually meaningful and they are actually helping to get to explain the variation in my response variable, because that is what is needed. If these variables are not at all important and they are not able to explain the variation in y, then why is this regression model even existing? Why should we consider this model even for like modeling purpose or for prediction purpose? So the variables that we have on our right hand side, that has to make complete sense in that sense, in terms of the fact that it has to in some way explain the variation in y. Okay, if we see that the variation that we have in y is not cannot be cannot be attributed to the variation in x, then maybe it's not a good idea to include that variable in the model, because this is presumed to have to not have significant effect on the response of interest. Okay, sorry. So in such a scenario where we want to justify or we want to test if the regression itself makes sense, or in other words, are these variables supposedly influencing y? Do these variations in these variables contribute to the total variation in y? If that is the question that I want to address, then the H naught is that all of these should be equal to 0. So beta 1 equal to beta 2 equal to beta k minus 1 equal to 0. Okay, so this means that none of the variables that I have considered is actually exerting any effect on the response of interest. So that means that these variables are not at all worthy of keeping in the model, and since all of these, I'm testing all of these together, this essentially means that the model doesn't make any sense. Okay, so this regression is a non-significant thing to do. Alright, now having said that, what should be the alternate hypothesis? So the alternate hypothesis in this case, H1, is not H0, or if I have to explain in words, that at least any beta j not equal to 0. So if at least even 1 is significant, then this hypothesis will be rejected. Okay, so this is the setup that we are working under, and we are going to test this using the ANOVA model that we have developed. Okay, so what do? We first consider an ANOVA table. Okay, so in order to do this sort of test, the first and foremost thing that we should be doing is considering the ANOVA table. Okay, so an ANOVA table looks like this. Here we are going to have sources of variation, then we'll have sum of squares, then we'll have mean squares, and then we have our F statistic. Okay, so let me just explain what each of these are. So in sources of variation, we have just two sources. So I'm going to write down, because I'm dividing it into two orthogonal components. So I'm going to write down, so source 1 is regression, source 2 is residuals, and here I have the total. Okay, then we have SS. So here I'm going to write the SS regression, here I'm going to write SS residuals, and then let me just write down the DFs as well, and here I have SS total. So the total sum of squares is partitioned into two orthogonal components like this and this. So when I'm talking about DF, I have n minus 1 degrees of freedom here, n minus k over here. Remember, the model is beta naught with an intercept beta 1 x1 plus beta k minus 1 xk minus 1 plus epsilon. Okay, so here it should be k minus 1, this minus this. Alright, and then we are going to calculate the corresponding MS. So MS due to regression would be SS regression by k minus 1, and MS due to residuals would be SS residuals divided by n minus k. And the F statistic is actually nothing but MS due to regression divided by MS due to residuals. Okay, this is what the ANOVA table looks like. Now once we have this ANOVA table in place, we are going to, our rejection rule will be this. So the rejection rule here is that we reject H0 if and only if F is greater than or equal to F alpha k minus 1 n minus k. So what is this F alpha k minus 1 n minus k? So this is essentially an F distribution, okay, with df1 as k minus 1, df2 as n minus k, and if alpha is that position, so let's say if alpha is this position such that the area above this point, this area is actually alpha. So this is actually called as the upper alpha point of an f k minus 1 n minus 1. N minus k, not n minus 1. Okay, so these sum of squares essentially are following chi-square distribution, and so chi-square divided by df and a ratio of two chi-squares divided by the corresponding df actually forms an f distribution. Okay, so this is what we have, and we are rejecting h naught if and only if f is greater than this thing. And if h naught is rejected, that means that at least one of the coefficients are non-zero. Okay, so this is how we devise an ANOVA table. Okay, so if I give you some problems, so let's say let me just write down a few problems so that we are absolutely sure about the calculations that go on. So here if I say that, let's say I have, so the question is I have a variable y equal to beta naught plus beta 1 x1 plus beta 3 x3 plus epsilon. So in this case I have k equal to 4, and what is k? K is the number of unknown params. Okay, so here SST will be how much? It will be summation yi minus y bar whole square. Okay, or you can write it as y transpose y minus summation yi whole square by n. S is due to regression is actually given by this beta hat transpose x transpose y minus, just wrote it down, minus summation yi square by n, and S is due to residuals is given by y prime y minus beta prime hat x prime y. Okay, so we can calculate this from data, and corresponding, if I have n equal to 20, let's say, then these df's will be 19, this df will be k minus 1, that is df will be 3, and ss residuals df will be n minus k, that is 16. Okay, so if we divide the corresponding sum of squares by their degrees of freedom, I'm going to land up at the MSs, and once I have the MSs, I can just do MS regression by MS residuals, and that will give me the F value, and the F alpha that I want to test, that would be given by QF, and then I'm going to do a one-sided test, so it will be always be greater than or equal to 0, so it will be QF 0.05, then DF1 will be 3, DF2 will be 16, and I should always specify here lower dot tail equal to false. So once I've given these in my R, then I'm going to get the value of F alpha, and then I'm going to see if my observed F exceeds F alpha or not. If it does, then I'm going to reject my H naught, and if it doesn't, then I will not reject the H naught. And then if I don't reject the H naught, that essentially means that the regression is not significant. Okay, because none of these variables are making sense, and that is why all of the hypothesis that all of these explanatory variables coefficients are 0, that means that the regression is actually not at all significant. Alright, so once we have this, we also learned about goodness of fit. Okay, so let me just bring it up here itself. So as an example, or as a metric of goodness of fit, we learnt about R square, or the coefficient of determination. Which is nothing but what? SS due to R square is actually SS due to regression by SST, or in other words 1 minus SS due to residuals divided by SST. Okay, this is actually called the coefficient of determination, and this actually assesses how good the fit is. Okay, so this essentially measures how well this regression, the fitted regression line, fits to the observed data. Okay, now one thing we'll have to keep a note over here is that R square is usually a preferred metric for goodness of fit if our model has an intercept term. If it doesn't, then there are other more preferred goodness of fit matrices, but in the presence of an intercept term, we should be using, we could use this R square, or coefficient of determination, as a valid metric for assessing goodness of fit of the data, which essentially translates to see how well the fitted line is actually explaining the observed data, or in other words, how much of the variation in my response variable y is being explained by the regression, and that is all that we are measuring with the help of R square. That is, what fraction of the total variance in y is being explained by my independent variables. And if a substantial proportion is being explained, then okay, I can say that yes, the regression makes sense, because these variables seem to be important. They seem to contribute to their variance, their inherent variation in those x's seem to contribute to the overall variation in the response variable. Okay, and in that sense, these are significant. Alright, so if I really want to write this term technically, then I should be writing it like this. So this should be 1 minus E transpose E. E is actually the residuals, y minus x beta hat, okay, and divided by so sorry, here I should write yes, okay, so this one divided by summation yi minus y bar whole square. Now we should note that 0 less than equal to r square less than equal to 1, and the closer to 1 we get, we say that the better we have fit our model to these observations. Alright, so this actually is measuring the explanatory power of the model, and in that way it is actually reflecting the goodness of fit of the model. Okay, so if I have to interpret the values of r square, then r square equal to 0 means very poor fit. Okay, r square equal to 1 means perfect fit or best fit. Alright, okay, r square equal to 0.95 should be explained like this, that 95% of the variance in y or in response is explained by all the explanatory variables. Okay, so mind you, number of parameters is number of unknown betas, but number of explanatory variables means number of x's. So in this particular situation, what I have been talking about for a little while now, so here in this case, if I consider beta naught to beta beta k minus 1 as k unknown parameters, I only had k minus 1 explanatory variables. Okay, so the x's here that we have, these are, where is it? So the x's are the explanatory variables. So what I mean to say is that in this particular model, number of explanatory variables, if anybody asks, because this is a model with intercept, number of explanatory variables is always 1 less than the number of unknown parameters. Okay, number of unknown parameters is beta naught to beta k minus 1, that is k, and number of explanatory variables is x1 to xk minus 1, that is k minus 1. Okay, so this was about the goodness of fit criteria, but this is actually uh, not the best metric to assess goodness of fit, mainly because this is not I mean this is not a very useful, I mean, I wouldn't say useful, this is not the most correct thing to do because of its involvement of this term epsilon E transpose E. So what this means is that since I have E transpose E is nothing but sum of squares of the residuals, okay? So this one actually means, let me just write a news. So R square equal to 1 minus SS due to residuals by SS total. This is 1 minus E transpose E by summation yi minus y bar whole square, okay? So this is actually 1 minus summation ipsa ei square by summation yi minus y bar whole square. Now, as I keep on adding variables to the model, this E prime E is going to reduce, okay? So what I mean to say is that if this is my partition SST equal to SS due to regression plus SS due to residuals, okay, if I add one more term, let's say in this model I had x1 to xk minus 1, okay. Now in this model if I just add x1 xk minus 1 plus xk, then what I'm doing is that I'm taking SST hash and this is SS regression hash plus SS residual hash prime, sorry, SST prime, SS regression prime plus SS res prime, such that SS res prime is less than SS res. Why? I am taking some variable, some sum of squares here, and then I am putting sum from here to here, okay. So addition of another variable leads to further partitioning of this sum of squares due to residuals, okay. So the problem with R square is this: if we keep on adding variables to the regression equation, then this residuals, sum of squares due to residuals is bound to decrease, okay, and that will in turn increase your R square. But indefinite inclusion of explanatory variables is not a good sign, because if those variables are irrelevant, then R square will increase and it will give us a very incorrect picture than what is actually happening in real life. So I may be including irrelevant variables, and I may be commenting that okay, this is explaining the variation too much, but it doesn't make any sense including irrelevant variables. Also, there's another concept that is called the concept of parsimony, which states that the simpler models with high amount of efficiency are always preferred over overly complicated models, okay. So if I keep on, in order just to increase R square, if I and to decrease the residuals, if I keep on increasing the number of variables that I have, that is actually not a good sign, and that will not help keep the model short, simple and effective. We always want to not overfit with taking whatever variables we have under the sun that we think could be important, okay. We take some and then we try to, so I mean this could also happen that we take a whole lot of variables and then we perform some variable selection or something like that, and then we land up at a smaller number of variables, and then we try to check how significantly these variables are explaining the variation in y. So indefinitely increasing independent variables in the model is surely going to decrease your sum of squares due to residuals, because it is helping to explain more and more of the variance, sure, but that will not give us a simple effective model. That is going to give us an overly complicated model, and some of which might be difficult to interpret, given the fact that some of these variables could be actually irrelevant and not at all influencing y. But for the sake of this goodness of fit metric, if we keep on including them, then we are going to actually falsify our data and paint a very false impression of what the data is trying to tell us. Okay, so now that we've understood this problem, what do we do as a solution? Okay, so solution here to this problem is that, so I'll just write it here. So r square, just a minute. So yes, so r square increases as number of explanatory variables increase. Okay, so if we keep on adding variables, r square is going to increase. But is it going to give me a good model? Perhaps no. So how do we circumvent this problem? So the solution is to use a separate metric. I wouldn't say the solution. So one solution would be to use adjusted r square, which is what, instead of considering SS regression by SS residuals, we consider MS 1 minus MS due to residuals by MS total. Okay. So this one is actually 1 minus SS due to residuals by n minus k by SST by n minus 1. So this is actually 1 minus n minus 1 by n minus k SS residuals divided by SST. Okay, so here, with the help of this factor n minus k, we are imposing some sort of a penalty. Okay, as k increases, n minus k is going to decrease, and in turn this quantity is going to increase, and that will lead to a lesser number of r square. Okay, so this is actually, this factor n minus k is actually putting a penalty for making a model complicated. Okay, but on the same time, SS residual will decrease if we keep on adding more models. So this one, the trade-off between n minus k, the penalty that is imposed upon including new variables, and the trade-off is with the fact that as we increase the number of explanatory variables in the model, my error sum of squares is going to decrease. So the trade-off between this residuals and the penalty for incorporating additional variables, that is going to keep the adjusted r square in check, and will unlike r square, which will keep on increasing, adjusted r square may or may not increase. So if it increases, well and good. That means that SS residual has decreased more than the penalty that has been imposed. So that essentially means that goes on to say that okay, this variable is actually important, and then this set should be kept as is. But if the penalty is more for including more number of uh, variables than the decrease in the residual sum of squares, then our adjusted r square is going to be less. Okay, so instead of using r square, perhaps a better metric is adjusted r square. Okay, because this will reduce if an extra variable is added, and that does not compensate for and that overtly compensates for the reduction of the sum of squares due to residuals. Okay, and another limitation is that adjusted r square can be negative also. Okay, r square cannot be negative. R square is bounded by 0 and 1. Okay, but adjusted r square, because of the correction factor, that that may be even negative. Okay, and if it is negative, then unfortunately there is no explanation that we can provide. Alright, so once we have this thing, another thing that we should keep in our mind, that if no intercept, then r square is not defined. Okay, and r square is not as robust because it is sensitive to outliers. Alright, so these are actually the limitations of r square. So what do we do if we have no intercept in the model? Then mostly what is done is that we consider different transformations or something like that. Okay, and then get the respective goodness of fit equations. Okay, so what I'm saying is that if there is no intercept, then r square is not defined. But if there is an intercept and we want to fit with the help of r square, maybe we can apply some sort of transformations, but we'll have to be extremely careful to check if the transformed variables and transformed r square is actually comparable with the original r square. Okay, so this part was covered in a little bit more detail in class, so I am just skipping over this. So once we have this, let us move on and find out how we can do these calculations in R. Okay, so I'm going to stop and reshare my screen, and I hope it will be visible to you. Okay, sorry, let me just file the new file. Okay, so let us use our favorite dataset, that is the empty cars dataset, to find out how we will be able to um, get the analysis of variance table, perform the significance test, and infer from that whether the model is significant or not, and then finally go on and assess the goodness of fit of the model. Okay, so let us first do that. Now here, if I consider the data set empty cars, let me see. Yes, so empty cars, n is actually n row of empty cars, that is number of cars that we are testing, so it is actually 32. All right, so I'll just remove these and then we'll go ahead. Okay, so n is actually 32. Fine. Now this is our data set where y is nothing but mpg, and x, let's say we consider cyl, disp, hp, and weight. Okay, let these be the 4 explanatory variables that we are talking about. So if I have to fit this thing, what am I going to do? The code is lm. Okay, so lm of empty cars dollar, or I can write this as mpg on cyl, disp, hp, wt, and data equal to empty cars. So this is going to give me, oh, what is this? Wt. Okay, sorry, I shouldn't give commas here. Here I should give plus, and then comma. So this is actually the regression line that I am talking about. Okay, now if I write this as model, okay, so if this is model, then if I do summary model, okay, let me just rerun. Okay, this model is a list of 12, and if I give a summary model, then I get these: the estimates, standard errors, t-value, p-value. Okay, and from here I am going to get the multiple r squared, that is the coefficient of determination, and from here I get the adjusted r square. Okay, and f statistic is actually giving me the f statistic that we talked about, and the dfs are k minus 1. So here k is 5, intercept 0, 1, intercept 1 2 3 4, so 4 plus 1 5, so k minus 1 is 4, and n minus k, 32 minus 5 is 27, and this is the p-value of the regression of the hypothesis, that whether the model is significant or not. If I want the ANOVA table, I am going to write ANOVA of my model, and here I get the ANOVA table. Okay, so this is a response. Alright, and this is the residuals, and these are like the individual tables. Okay, so if I have to construct from this ANOVA table, the ANOVA table that we want, so here if I just write the ANOVA table, then here if I have to write sources, DF, SS, MS, and then the F statistic. Okay, so sources, one is regression, and the one is residuals, and the one is total. So n minus 1 total DF would be 31, residuals is actually 32 minus 5, that is 27, regression is k minus 1, that is 4. Okay, sum of squares, we'll have to add all of these up, so that would be 817.71. so let me find out. 817.71 plus 37.59 plus 9.37 plus 90.92. Okay, so this one is actually SS, so it would be 955.59, and SS due to residuals is actually 170.44. so total it will add up to 1126.03. so this is 1126.03. okay, and MS is what? This is equal to okay, so MS is actually this thing divided by 4, 238.89, 238.89, and this one is nothing but only the residuals, so it will be 170.44 divided by 27, so this is 6.31, 6.31. okay, and this one is total, so this will be this total thing divided by 31 n minus 1. This is 36.32. Okay, so f is actually then 238.39. okay, so f is actually this thing divided by 170.44 divided by 27. Okay, so this is f 37.844. so let's see if it matches or not with summary model. Yes, it's 37.84 and this is also 37.84. okay, so f is actually 37.84, and then we'll have to find out with respect to the p-value. Okay, so p-value is pf q, that is 37.84, df1 equal to, so df1 is 4, df2 is 27, and lower dot tail equal to false. So this is 1 into 10 to the power minus 10, and that is the p-value, 1 into 10 to the power minus 10. So this is p-value. Alright, that is probability of, so p-value in this case for analysis of variance is to be calculated in this manner. Just a minute. So here p-value is probability f greater than f observed. Okay, and that is f n1, sorry, f k minus 1 k minus 1 n minus k. This is the p-value. So that is what I exactly did. I am finding the probability that f exceeds this one, and since I am trying to find out greater than equal to, I'll have to give lower dot tail equal to false, and that's the p-value. And if I want the upper alpha point, then that is given by qf 0.05, okay, 427, and then lower dot tail equal to false. So then this one upper alpha point is actually, so critical point is 2.72, and f observed is how much? F observed is 37.84, so which is greater than the critical point, hence we are rejecting H0, which means to say that the model is significant. Okay, and also p-value, same thing, either we talk in terms of the critical value or in terms of the p-value. So if we see a p-value is also less than 0.05, that is my desired level of significance alpha, then so also, I mean, it is bound to happen, it will not happen that this satisfies and this does not. both will happen simultaneously. So also p value is less than alpha, so reject h naught and conclude that the model is significant. In other words, that all of the variables that we've considered, the variation in them is actually helping to explain the variation in the miles per gallon. Okay, and from here we also learned how to get the how to get the adjusted r square and the r square values. All right, so yes, now once we have that, let us just learn about a few more topics which were covered in this session, which were on multicollinearity, ridge regression, and another regression that we learnt about, that is called lasso. Okay, so we'll briefly touch up on these topics before ending today's session. All right, so so far if I am given a regression equation, I should be able to find out how to get the estimates, how to find confidence intervals, how to get the value of the adjusted r square, how to get the value of r square, how to find the residual sigma square hat. So sigma square hat, here in this sigma square hat is actually ms due to residuals. Okay, that is what it is. And the adjusted r square, what will happen to r square if the intercept is not present? How do we find the f statistic, and what is the decision about the null hypothesis? What is the null hypothesis that is being tested, and how to find out mean squares due to variables and combined due to regression. Okay, due to individual variables, you are going to find it here. When once you do a ANOVA model, then these are going to give you the individual mean squares for the respective explanatory variables. Okay, okay, so now that we have this in place, let us quickly learn about lasso, ridge regression and multicollinearity, and see how we can perform them using R. Alright, so usually ridge regression and lasso is applied for variable selection. Okay, especially lasso is applied when we want to have some variable selection. What happens is that we might have a large number of explanatory variables, and then we'll have to, we don't want to include everything in our model. We just want to have a few significant ones that actually contribute to the variation. Okay, because we want to keep the model very simple and effective. That is the whole purpose of doing a regression, not including everything and anything that is there and that could be possible. All right. Right. So we have, the challenge to us is that we'll have to select from a pool of variables. We'll have to select the ones which are crucial, or which are sort of important variables for our regression. Just a minute, excuse me. Okay, sorry. So why do we need to perform variable selection? A, we want to keep the model very simple and effective. Secondly, if we include a large number of variables which contribute some, very small quantities to the total variance, then what actually happens is that while we go for inversion of the matrix to get the OLS estimates, that time there could be some sort of troubles. Okay, it could be a computational trouble because inversion of high order matrices may be difficult, or there could be some other issues where the assumption that the x's are independent, that is violated. Okay, that might also happen if we have very large number of x's, some of which are sort of related or correlated with one another. Okay, so that is why we should have some sort of variable selection in place. Okay, now so what I was saying is that if I have a large number of explanatory variables, then chances of multicollinearity increases. Okay, and multicollinearity means if this is my model matrix, this is the intercept 1 1 1 1 1, and then if we have x1 something, say x1 1 2 xn1, and then we have xk minus 1, so xk minus 1 1 2 xk minus 1, or xk minus 1 n, something like this. So if we find there could be high amount of correlation between these two columns. Okay, so correlation x1 and x2 could be high. So if we keep on including more terms, xk plus 1, xk plus j, something like this, so these pairwise correlations may, I mean there are chances of having such pairwise correlations increase. And if we have something like this, if we have correlated matrices where columns are correlated, then the rank of the matrix will not remain, the matrix will not remain a full rank matrix, and then inversion of these sort of matrices will become a very difficult affair to manage. So that is the reason why we should have, that is yet another reason why we should have some variable selection in place. Okay, so in case of ridge regression, what we do is, so if we have something like this, if we have a ridge regression, what is it doing? It is actually finding out beta hat ridge is actually minimizing this quantity yi minus xi prime or xi beta whole square summation I equal to 1 to n, subject to this criteria or this penalty, that is summation bj square j equal to 1 to, let's say, k is less than equal to t star for some t star greater than 0. Okay, so this, if this quantity is to be satisfied, there are several considerations here. So t star, if it is too low, if it is very very close to 0, then almost all the betas will be pushed more towards 0, because this is summation beta j square. Okay, so if t star is very very small, then all beta j's would be sort of pushed towards 0, right? And by using this sort of regression, we can get rid of multicollinearity. And how do we do that? So in order to do this minimization, this is actually incorporated as argmin, or we are minimizing summation yi minus xi prime beta whole square plus lambda summation bj square j equal to 1 to k. Okay, and in that case the RSS can be written as y minus x beta transpose y minus x beta plus lambda beta prime beta. Okay, and if we just do del RSS by del beta and then we equate it to 0, then we have beta hat ridge as x prime x plus lambda I inverse x prime y. So because of multicollinearity, x prime x was not invertible. So what we are doing here is that we are introducing this lambda I, and that is again making this matrix sort of a full rank matrix, and then we are able to do this inverse calculation. Okay, so this singularity, when we have a large number of correlated rows, that is avoided by adding some values to the diagonals and then removing the singularity, and then inversion is possible, and then we get the ridge estimate. Okay, so this ridge regression is actually a way of tackling the multicollinearity problem. All right, and but then the question is, how do we choose lambda? So usually what we do, we give a sequence of lambdas and then choose one such that it's not too large or it's not too small, or some reasonable choice of lambda is also made based on the domain that you are applying this regression to. Okay, and then we lastly learn about lasso, which is very similar to ridge, but here we are actually minimizing summation yi minus xi beta whole square I equal to 1 to n, but subject to the criteria that summation beta j equal to 1 to k is less than equal to, absolute value of beta j is less than equal to t star for some t star greater than equal to 0. So now the thing is, since it is, if this t star is very very close to 0, then beta j's will, because these are absolute values, beta j's are bound to be 0. So what it is doing is that placing this condition, this regularization condition, we are shrinking some values of beta to 0. I mean, by choosing this t star, we will be able to shrink some values of beta j to 0, and that will help us choose the non-zero beta j's, and that will in turn help in variable selection. Okay, so this choice is crucial, and that also, I mean, depends a lot on the domain and those kind of things that we do. So usually we use the system of cross validation, okay, where the sample is divided into two sets, training and test. So maybe we make 5 folds, okay, and then use 4 for training, 1 for testing, and repeat it 5 times, and then based on what we have as our lambda, or what we, I mean, based on that we make choices on the t dash. Okay, so theoretically the RSS in case of lasso, sorry, yeah, so so the RSS in that case, lambda k, becomes summation yi minus summation j equal to 1 to k beta hat k lambda s xij. Okay, I'll not go into these details because this is a little difficult to understand why these expressions are coming, but in practice what we do is we divide this into blocks and do some sort of cross validation, in the sense that we get the RSS for each block. So what we do is that we partition into blocks, okay, 5 or 10, then we get RSS for each block, and then we do an average RSS, okay, and then we find the lambda that gives minimum RSS, minimum average RSS. Alright, so how do we use the software to do this? So in order to use the software, we use this package which is called iLasso. Alright, so the thing is, if I go and do install dot packages iLasso, then they say that this is not available for this version. So what do? We actually go to this CRAN. I have typed iLasso here, and I'll go to this CRAN project, and there I see that this is actually deprecated right now, but it is formerly available versions can be obtained from archive. So if we have some packages which are currently removed but available in archive, then we need to go to this archive, and then we can select each of the versions. So let me say this is the latest one, 21/6/2018, and I suppose I want to install this. So I'm going to do this copy link address, and then instead of install all packages and the package name, I am going to write install.packages, and then I'm going to give this link, hyperlink, and then this is going to get installed. See, this is done. This installation might stop if there are some other dependencies, in the sense that if this package, to build this package, some other package is also required, you first need to install them and then finally go ahead and install these. Okay, so once I have this package, I am going to write library iLasso, and it's loaded in memory. And then once I have this, all I need to do is that I need to find out. So the first thing that I need to do is I need to specify the X matrix, right? So how do I do that? How do I specify the X matrix? So here the function that I'm going to use is the lasso function. If I press F1, I am going to find out more about this function on my help page. Okay, fit a model using a design matrix. So this is a matrix of explanatory variables. So how do I construct a matrix of explanatory variables? So I can do one thing. I already have this model. So let me see. If I give x equal to model dot matrix model, what do I get? So x will look something like this. It will have the intercept term. Let me just do away with this intercept, and so it will be comma all rows -1. So let me see how the x model looks like. Okay, so this is my x. So if I put x here, and then if I put y, that is empty cars $mpg, that is my y, and I put family equal to Gaussian. Okay, IMPL implementation equal to CPP. Okay, and then I provide something similar. Lambda mean ratio is this, lambda equal to lam or something like this. If I put it here, and if I give lambda equal to a sequence, or let's see what happens if I give this. Okay, so family, yes. So if I give this, I get this equation. So n lambda, they have generated 100. I'll just do with 5. Let me see. So here I have estimates of beta standard. So 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 1 2 3 4 for the 4 explanatory variables that I have. Okay, and these are those corresponding 5 lambdas. Okay, now this one is a little difficult. I mean, none of the variables have been shrunk to 0. Alpha is the new intercept that we have over here, and from here we'll have to choose the lambdas, and then once we have chosen the lambda, then we'll have to put this alpha and the corresponding beta set, and that will be our lasso regression. Okay, so corresponding to the third lambda value, if I want to have a standardized beta estimate, then I'll have to look into this column 3. If I want to have the estimate, standardized estimates with respect to the fourth one, then I'll have to look into the fourth column. All right, and if I just want the beta estimates, then these are also given with the corresponding variables. Okay, and the lambdas. So mind you, whenever it is standardized, it means that it is the variables are, the x variables are x minus mean by st, standard deviation. But here we have the raw variables, and if we want the estimated betas, then we should look into this beta column. Okay, and the estimated alpha corresponding to any value of lambda is this one, the alpha 1 parameter. Sorry, it's not the alpha 1 parameter, it's the A0 parameter. Extremely sorry. So this is something else. So if you are asked that what is the intercept corresponding to third lambda, then 42.40587 is your answer with respect to the third lambda. Okay, so A0 column is actually a0 gives the respective intercepts corresponding to lambdas. Okay, now how we are going to choose lambda, that is dependent on the experimenter or the person who is actually carrying this work out, and also it might also depend on the domain where you are applying. So some amount of experience is also required to do this. Alright, so with that I am going to end today's session. I hope this was helpful and you'll be able to solve the assignment questions based on whatever we discussed today, and also also with the study material that is available. So please do not hesitate to post in the discussion forum if you need further clarifications. All right, thank you so much for listening to this, and I'll see you in the next session. Thank you.